All right, let's pick up where we left off. I know I got cut off abruptly there. So I'm back on the first page, and I want to write down that final result of the electron energy, okay? And you can put it, actually, I don't want you to write it in this box just yet, but let me write the long form here because there's a modification to do. So we're basically saying is the energy of an electron at a particular energy level, okay, is equal to negative, and that we've seen it negative in our reference tables. That just means it's a negative total energy. It's bound. 2 pi squared, okay, K, again, Coulomb's constant, e to the fourth, times the mass of an electron, so maybe I'll put a little e there, all divided by Planck's constant squared, and then the important part, 1 over n squared. Now, I'm going to write over here, and I don't expect you to, the equation you have at the very top of the page, that one that had been known for a while that Bohr was trying to figure out where it came from. 1 over lambda equals r, right, 1 over n squared minus 1 over small n squared. And I want you to notice what they have in similar, what they're similar about them. And the key thing is this n part. So we see, oh, I'm sure that shouldn't say n2, that should say n squared. And what I want you to understand is the key insight here, that what was made people take notice, is Bohr was able to get that 1 over n squared part here. The reason we have one minus the other is if I just want to talk about energy changes. But if I want to understand what energy an electron has at a particular level, then I just put in whatever level we're at. If we're at the ground state, we put in a 1 there. If we want to talk about a transition from, let's say, 1 to 2 or 2 to 1, then that's where we use this part right here. The R is clearly related to all of this. It's not quite the same thing because here we have energy, here we have 1 over lambda, but we can easily see that energy is hc over lambda. So 1 over lambda, if we move the hc over to here, then we can get the Rydberg constant. Not that you have to do that, okay? But people could do that, and they said, Bohr has to be onto something. He's just solved this decade-old problem using this odd combination of quantum and classical. Now, here's the part that I do want you to write down, and this is in your IB reference tables, is if I take all these constants, and I suggest you do that. I'm not going to do that here, but you put in Coulomb's constant, the charge of an electron, the mass of an electron, and Planck's constant, and you convert that to electron volts, because I believe if you do it like this, you will get it in joules. But if you convert the electron volts, you'll find that that number is negative 13.6. And then we have the 1 over n squared. And that 13.6 is exactly what we saw in our previous note sheet, what the ground state energy is for electron and hydrogen. That's pretty remarkable. And the n squared means if I want to go to the second energy level, right, I put a 2 in there, then it's going to be 13.6 divided by 2, and we should get the number that we get for n2. So that's the beauty of what Bohr was able to do. So this is a simple way of calculating the electron energy level. That's the equation that's in reference tables. You want to understand where it comes from. Okay, you don't have to derive this as far as I know, but what you do need to know, and I'll summarize this next page, this all comes from an assumption Bohr made, and that was the quantization of angular momentum. So let's turn to, next page. Summarize this, okay? So what was Bohr's physical basis for saying that? Well, first of all, his theory was technically called ad hoc. Ad hoc is just a Latin way of saying we just kind of threw some pieces together without any real basis for that. In other words, he made assumptions. He had no reason to make those assumptions other than after the fact they worked. Okay? It wasn't until about a decade later, not quite a full decade, that de Broglie came along. We've already talked about de Broglie, and gave the physical basis. Okay, so how was de Broglie's theory able to, after the fact, explain Bohr's theory? Well, let's recall what the de Broglie wavelength is, right? Lambda is h over p, and for an electron, that's going to be h over mv. Whoops. Okay, so he applied this to an electron by stating that the orbit, now this is a really interesting thing. So now, if de Broglie is hypothesizing, okay, if electron can have wave-like properties, a wavelength, and electrons are found in orbits amongst other things, then if I'm going to have a complete orbit, so let's say this is the nucleus, and I want to form an orbit, the orbit is actually a standing wave of a full integer of the wavelength. In other words, the first and simplest orbit we can get is nothing more such that the circumference, and that's a little bit simplistic, is nothing more than the wavelength. Anything other than that wavelength isn't going to happen because that orbit can't close upon itself. And then the next energy level is going to be, if you will, this is n equals 1, that's the fundamental, will be a variation of that. It would be like the second harmonic. And here you can see down in this chart is what a two-dimensional standing wave would look like if we have the Bohr model. So the Bohr model for an electron orbit, if this is n is 1, here is n is 2, n is 3, n is 4. The point is these standing waves are simply multiples of the de Broglie wavelength of an electron. So that's kind of a really cool interpretation because it brings in integers, because standing waves are all about integers in terms of the fundamentals. Sorry, I don't know what just happened here. Okay? And so now we can see mathematically what's going on. So let me fill in the blanks here. So this is actually a standing wave whose circumference is a whole number, an integer, of the electron wavelength. All right, that's crazy, but it makes sense if you think about it. So how do we apply this? Well, we're going to apply to Bohr's theory. So remember, we got a full circumference. So the full circumference of a standing wave is 2 pi times that r for a particular energy level. And that's got to say equal to n, some integer, times the de Broglie wavelength. And what is the de Broglie wavelength equal to? Well, we see up here, that's going to be n h over mv. So if I move things around, I see that mvr, oh gosh, that's our angular momentum, equals n h over 2 pi. And if you go to the first page, you'll see exactly that's what Bohr assumed almost a decade earlier without any physical basis. So that's pretty remarkable. So this derivation is fairly straightforward if you know where you're trying to end up. Okay, so summary. These are the three postulates of the Bohr model. We've already talked about them. First and foremost, and the most important thing, electrons are found only in well-defined orbitals that do not, give off energy. In other words, if these electrons are going around and around, classical theory says they're accelerating centripetally, so they have to give off radiation by Maxwell's theory. Bohr said no. For whatever reason, they just don't give off the energy. These stable orbits, that word stable is implying that we're not giving off energy, are defined by those whose angular momentum is quantized. And I just showed you after the fact rationale for why it would be quantized based on the electron wavelength and a standing wave, or the equivalent standing wave. And when electrons move between stable orbits, they absorb energy. That's when we go from low to high. We've already done problems with this. Or they emit energy when they go from high to low. And we get photons of particular frequencies, photons of particular energies, which mean they have different particular frequencies, which means they have particular colors, which explain the spectrum of hydrogen. So, limitations. What wasn't perfect about it? And this is a major failing, but that's all right. It failed to predict the emission spectrum for atoms with more than one electron. Simply put, it could not explain the spectrum for helium, or lithium, or beryllium, or boron, carbon, etc., etc. That would come later with Heisenberg uncertainty principle, which wasn't developed until the 1930s, and Schrodinger's equation, etc. And also, it wasn't able to account for the relative brightness nor fine structure of the spectral lines. Brightness, in other words, if you look at spectral lines, you'll know some were brighter than others. This model couldn't explain that. That came later in something called fine structure of spectral lines, which has something to do with when you apply a magnetic field to the atom, you will see some splitting of lines, something called the Zeeman effect. But just understand that his model wasn't perfect, but boy, if it could explain hydrogen and incorporate the quantum aspects of things, there was something to it. Okay, so I'm going to finish up with this. I don't think this is on your note sheet, but I want you to, something I believe you saw when you were in chemistry. These are representations of electron orbital levels. Remember S and the P levels and the D levels from chemistry? Okay, so this is the simplest. This is one electron. And this is the idea of an electron cloud. In other words, you can't define exactly where an electron is, and that comes out of Heisenberg's uncertainty principle. So what I want you to understand, and this is trying to pull everything together at this point right now, is this shape, in this case, a very simple sphere. So we're pretty positive the electron, where it's darkest, is the most likely place where the electron is going to be. All this, or these shapes when I have two electrons, there's three different variations of that, come from Schrodinger's equation applied to Bohr's model of atom. Remember, Schrodinger's equations is really about a probability wave, that superposition of probabilities based on certain properties of the electron. So when you apply that to this model, you get these different electron cloud configurations, which ultimately explains the orbital configurations of electrons, which ultimately explains all of chemistry. Okay? So it's the quantum developments as applied to light, and then to electrons, and electrons to atoms, and then other aspects that ultimately give us the full description of how atoms behave, the bondings they make, the spectral lines, etc. And that's pretty satisfying to have at least a superficial understanding of where this originates. Okay, so there is a homework that follows. I'll probably assign that later. But as always, come in with questions because there's a lot of little detail here.